magic that I showed you. And the second bit of related magic, although I didn't relate them, we'll relate them today, I showed you is that if you just think about Feynman diagrams, you're just supposed to add different terms. This diagram, that diagram, that diagram. You're supposed to add all of them up together. There's no obvious sense in which this diagram is related to that diagram, or this diagram is close or far, nothing. They're just different things, different numbers, and you add them all up. And yet, what we did is uplift every term in the Feynman diagram expansion to a differential form instead. So instead of writing down 1 over propagators, we wrote down d log of all the propagators. And then there's this remarkable fact that it's possible to assign signs to every one of those terms in such a way that the entire differential form is actually secretly only a function of the ratios of the kinematic invariant. So that's what we call projectivity. Now that's a miraculous seeming fact, just algebraically, because if you just count equations and unknowns, there are vastly more equations than unknowns in order to fix all the signs. So it's kind of a miraculous fact that it's possible to assign signs to all those different pieces in the differential form for this fact for this fact to work. And I'll sketch quickly, and we'll probably flesh this out more on Thursday when we really talk about the connection to the ideas of cluster algebras. But at least I sketched how just that picture of why the form is projective suggests that you should think about some diagrams as being close to other diagrams, okay? Because when you do this, when you do the projective variation, of the form, you find that you have to have the coefficient not of all the d logs of all propagators but 1. They have to add up to 0, and it's just a fact that there's precisely 2 diagrams that have one fixed set of n minus 4 propagators in them. And therefore, if you want the signs to add up, you have to, if you start with one sign for one of them, then the one where you just flip one of the propagators to another has got to have the negative sign. Then you've got to flip another one that's got to have a positive sign, a negative sign. So there's this way to walk through everything, and that assigns signs to everybody, and you're done. And then it's just a miracle that it works for all the rest of them. Okay, so this is a very non-trivial fact that this is possible, but it gives you an idea that you should not be thinking about amplitudes as numbers, again, but somehow thinking about them as forms is exposing more hidden facts that are not obvious in the way they're spat out to us by the pathinogram. Okay, so all of that was motivation. All of that was motivation that there's something going on even in boring old planar phi cube theory. And so today what I want to do is, again, go back, take the same sort of philosophy that we had for the amplituhedron, and go to the kinematic space associated with this scattering process, stare at the kinematic space for a little while, and then ask a question in that kinematic space whose answer is going to turn out to be the tree scattering amplitudes for this theory. So that's what we'll talk about today. An extension of these ideas, by the way, this is all work that's actually, the connection between phi cube theory and the associahedron goes back 2 years by now. I probably won't have time to talk about it unless anyone wants to come back for a super duper bonus informal last after lecture where I'll talk about the connection of all these things with string theory. So they're very intimately connected to string amplitudes. All this collection of ideas are around the same, the same thing. But anyway, that will be really unofficial. But the connection between phi cube theory and the associahedron goes back, this explicit connection I'm talking about goes back 2 years. The particular way that we'll derive it is actually new and should hopefully come out by before the end of the year. Okay, so and it also works in the simple way that I'm going to talk about. It works to one loop order. Okay, so we can do up to 1 loop amplitudes for phi cube theory, and as I mentioned last time, or I alluded to last time, attempting to make sense of this to all loop order is something that we've been trying to do, and I think also interacts in a very interesting way with some novel structures in cluster algebras, which you'll at least get some taste of next time. Okay, but today we're just doing very simple things. So first, let's remind ourselves what the What is a kinematic space? The kinematic space we're talking about So as usual, we have n particle scattering. We have our ordering, and we defined these variables from I to j, xij, which are pi plus dot dot plus pj minus 1 squared. So these are chords on our favorite polygon. Okay? So our kinematic space is just the space of the xij. And as I reviewed last time, the number of xij's, which is equal to n choose 2 minus n, which is nn minus 3 over 2, is also equal to the number of independent Mandel-Sam invariants. So these are not only beautiful variables associated with the poles of cubic graphs, they're also a basis for all the Mandel-Sam invariants. Okay? So there's something very, very nice about them. Okay. Now, there's a lovely thing about these xij's. As we've said, as we stressed already, using the xij's, there's something nice, which is there's always slightly annoying if I wanted to talk about, I don't know, this propagator. I could either say that it's p1 plus p2 squared, but that's the same as p3 plus p4 plus p5 squared. Right? So using the x's is nice. We just call both of them x13, right? They're just associated with the chord that cuts the polygon in two, okay? But we still have the little extra thing that we have to add, that xij is the same as xji. So it's sort of better than before. It only depends on the chord, but the ordering of the I and j doesn't matter, right? So, okay. So our first item of business is then to just try to represent the kinematic space, right? So I just want to represent all of these x's, but I want to represent it in a way that makes the cyclic symmetry obvious, right? And the fact that xij is the same as xji. And already when you think about this, there's this. It's slightly interesting. Okay, so let's try to draw a picture for kinematic space. Here's a picture for kinematic space for I don't know, n equals 7, n equals 8. I want to make it big enough so that okay. Now just for convenience, I'm going to include in the picture the xii plus 1s. Now, these are 0, okay? Xi plus 1 is 0. That's exactly the null momenta on the outside, okay? But I'm just going to find it convenient to add the xii plus 1. Okay, so I'll denote them with an open circle. Okay, so here's how I'm going to do it. Now, obviously, this is going to be a grid, right? It's going to be a grid. Because I have to represent the ij indices. All I'm doing here is representing ij indices. So it's going to be a lattice of just ij indices, but I'm going to draw it, tilt it over by 45 degrees for reasons that'll be clear later. Okay, so there's nothing deep about drawing it as 45 degrees. It's just a lattice. The slightly interesting thing is to see how the cyclic structure on the xij equals xji is reflected in the lattice. So. But anyway, I'm going to draw it like this. So this is going to be the variable x12, and then x13, x14, x15, x16, x17, and x18, which is also a 0, right? Okay, and then, so this is going to be the direction of x1j with increasing j, right? So starting with 2 and going all the way up to 8. Okay, so then this guy here is going to be x23, okay, and so on, right? So this will be x24, x25, x26, x27, x28. Oops, I see I've already screwed it up. Okay, So is it clear what we're doing here, right? So now, so I'm just going to keep on going like this. I'm making a mesh. Oh boy. Ugh. Wow. This would be x3, 4, x4, 5, x5, 6, x6, 7, and so on, right? And the picture goes in both directions. So, and in fact, the way I've drawn it, so here is the sort of so the whole picture sort of lives in a strip here. The whole picture lives in a strip like that. And so in the strip, I have captured all of the xij's, and I've made it so that the cyclic symmetry is obvious, right? Cycling everything over by 1. But I get xij and xji appear both in this picture, right? So for example, here I have x14, but we'll see x41 out there somewhere. Okay, so we have both xij and xji in this picture. Let's say you want to just capture one copy of all the xij's, right? So not xij and xji together. Then you have to take a chunk out of this picture. And there are many ways of doing it. I'll say what the general way of doing it is in a second. But one way of just choosing xij and not xji, one way of choosing a chunk which covers xij versus ji just exactly once is to, for example, take this. Okay, so here I would have 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, I'll put 1, 8 here. But then okay, if I fill in the rest of the picture, this would be 2, 3, 2, 4, 2, 5. This is 1, 8. And then we go up here, we get 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, and 7, 8 up here. And so you see precisely by stopping here, if I went one over, I would have 8, 1. Right, but I already have the 1, 8 down here in the picture. I have a 1, 7. If I kept going over here, I'd have a 7, 2. Okay, so if I want to just keep everything where the xij versus the xji is covered once, I have to take something like this. This is one example. I could do other, I can take many chunks out of this infinite mesh that cover all of xij or xji precisely once. Okay, this is a particularly simple one. Okay, so now, what would happen if we wanted to go from 8 particles to 100 particles? Okay, well, I mean, I would just draw a similar mesh. It would just get denser and denser and denser. Okay, so it's actually convenient if I want to imagine treating all particles in one go to just imagine the whole picture as a strip, as a continuous strip. This is not saying it's actually continuous. It's just saying that I think of kinematic space just abstractly is this continuous strip, and then if I want to choose any n, I have to just plonk down some integer lattice on it with these 45-degree lines. Okay, so let me first give you the description of what the infinite n kinematic space is. Okay, so infinite n kinematic space is just this infinite strip. Okay? I'm going to call this direction t and this direction x. Later we'll interpret these as time and space, okay, in some auxiliary. This isn't kinematic space, not space-time. This is some funny kinematic space, but just for now. But all I want you to see is what is this I? If this point here, if this point t comma x is labeling ij, where is the ji point? Ji is 1 plus t and 1 minus x. If this thing has, if I just define it to have width 1. Okay, so that's the ij to ji identification. Okay, so I have a sort of a Mobius strip here. I have an infinite strip, but if I want to cover, but the ij to ji identification is making this Mobius identification on the infinite strip, together with the cyclic rotation, right? But the cyclic rotation here, the cyclic rotation has width 2. Because in order to just cycle everything over, all the indices over 1, if I just do it, cycling over 1 is not taking ij back to ij, it's taking ij to ji. So if I want it to come back again, I have to cycle it over by 2. Is that clear? And that's, okay, so we have a literal identification of something of width 2 in this picture. Okay, there's a Mobius identification, and the cyclic rotation that cycles all the indices over comes back to itself when we shift everything over by 2. Okay? So this is the cyclic. That's the cyclic shift. Okay. And now, if I want to cover ij and not ji in this picture, so if I want to take out a chunk that covers ij and not ji, then I just choose any curve here, C. I choose any curve on the other side. I'll call, drawing it badly, any curve on the other side, I'll call C bar. The curve C bar is what I get. Take C, shift 1 to the right, and turn upside down. So that's exactly what this tx, the 1 plus t, 1 minus x transformation is doing. It's identifying a point here with a point there. And so if I take anything in this region, everything in that region will cover ij and not ji. Okay, so in the continuum, that's what I want to do. Okay, so I want to take a curve, and in the language of time and space, I want to take a space-like curve and shift it over by 1 in time and turn it upside down. And anything that is captured between them is going to cover ij and not ji. So we're just practicing with what kinematic space is. Okay? So there's many ways of picking out there isn't a way of seeing all the symmetries manifest, okay, because of this slight annoyance that ij and ji are the same thing. If you want to cover things non-redundantly, the thing which is perfectly symmetrical is the whole strip, but then you have to make a choice to take a chunk out of the strip that covers ij and not ji. Okay, so far so good? An extreme limit of this is the simple case where C actually becomes null. So if this is C, then C bar is just that. Okay, C bar, which is translating over by 1 and turning upside down, becomes this, and that's just the picture that we talked about there. Okay, so this now has width 2, and this has 1, and so the inside of that region is exactly what we talked about in that simple example. Okay? So far, so good. We're just talking about, there's almost nothing interesting going on here. It's just a way of plonking down ij, right? You know, we just have a two-dimensional space of kinematic invariance, ij. We want to allow ourselves the freedom to talk about any number of particles, so we go to the continuum. And the only little subtlety is how to make sure we cover ij and not Ji. Okay, and so already that, but this is our canvas now. Okay, our canvas is this kinematic space. Okay. Pretty boring place, right? What the hell are we supposed to do here? Right? Okay, just like n 4 vectors in momentum twistor space is a pretty boring place. And what the hell were we supposed to do there? Well, we managed in the kinematic space of n 4 vectors to find some injection of the word positivity in order to bring to life all of the structure of planar n equals 4 super Yang mills. Okay? So now we're going to do something analogous here. Okay? We're going to ask a question in this kinematic space, just on the strip. That's all. We're going to ask a question on the strip. And the answer to this question will end up in a very similar way, giving us the amplitudes for phi cube theory. Along the way, we'll discover the associahedron. And after we play around a little bit with what we're doing, we'll also get a clue as to what these generalized cluster associahedra are. OK, any questions so far? Almost nothing interesting has happened yet. So we're just setting up. But any questions so far? OK, good. So now let's forget about all of this. Since our canvas is just this two-dimensional space, the question that we're going to ask in this two-dimensional space is going to end up being, oh, but sorry, let me tell you what the goal is. So what are we supposed to make obvious? Sorry, let me just stress again. What we'd like to make obvious is that, remember, we have amplitudes that are associated with these cubic graphs or the triangulations of the polygon. It is not obvious that the triangulations of the polygon are vertices of this associahedron. I told you it's a mathematical fact, but it's not an obvious fact. Okay? It's not obvious that the combinatorics of the compatible chords in the triangulation of a polygon is polytopal, and it's not obvious that that polytope factorizes on the boundaries. What we'd like is some picture, ultimately for the amplitudes, which makes it obvious that it's polytopal and that it factorizes. That's what we want to make obvious. So we want to make all those facts just completely manifest from some simple picture. Okay? That is our goal. Remember, some things make just factorization obvious. Feynman diagrams make factorization obvious. The string worldsheet makes factorization obvious. They don't make the polytopal nature of the combinatorics obvious. We want to make everything obvious, both the polytopal nature of the combinatorics and factorization. So that is our goal. Okay? And that's what we're going to do in the next half hour. Okay, but to begin with, let's talk about the wave equation in 1 + 1 dimensions. Okay? So again, it doesn't much matter what I call time and space in 1 + 1 dimensions because everything is symmetrical anyway. But I'm gonna imagine this is time and space. So the normal wave equation is dt squared minus dx squared of some variable that I'll call capital X equals 0, right? But let me allow myself a source as well. And I'll call the source little c of x and t. Right? So that's the usual wave equation. And let's immediately transform to u and v variables, the light cone variables, which are x plus or minus t. And we know in terms of u and v, the wave equation becomes du dv x equals c of u and v now. Right? Okay. Now let me review a few things about the wave equation. First, how do we solve the wave equation? Well, what you're used to doing from whenever you learn it, if you're a European kindergarten, I guess, if you're American sometime as a sophomore in college, is that well, the Americans catch up quickly, or at least they used to. is that you're supposed to give boundary conditions on some surface and the time derivative there, and then you can predict the future, of course, right? It's actually going to be convenient for us to present it in a different way. We're going to be interested in boundary defined on causal diamonds. Okay, so this is a picture of a causal diamond, right? So here's some event. Time is going this way, so the waves go in this direction. Here's two space-like separated points, and then so this is the causal diamond associated with these two time-like separated points is this picture, right? So it's the intersection of the future light cone out of the point A with the past light cone of the point B. Okay? And something that's quite obvious, and I'll give you the reason for it in a second, is that if you give me the data on the boundary of the causal diamond, in other words, just give me x, nothing about x dot. You just give me x on the boundary of this causal diamond. So x of, if you like, x of if you give me x on these boundaries or on these boundaries, if you give me x on any boundaries of this causal diamond, I can fully determine what x is on the inside. And actually, let me give you the immediate general reason for this, which is just the following. Let's say that the value of x here is x at A, x at B, x at C, and x at D. Okay? Then there's a Gauss law associated with the wave equation. The integral form of the wave equation is very simply that xa plus xb minus xc minus xd is equal to the total current. The integral of c on the inside of this diamond. Okay? That's very easy to derive. In fact, you can think of this Gauss law as the fundamental integral equation, the fundamental fact. If you squeeze the diamond to zero size, then the Gauss law turns into the wave equation, right? Because exactly xa plus xb minus xe minus xd is the du dv derivative. So I get du dv equals c, just like you were used to in going from the integral to the differential form of the Gauss law in electrodynamics. The thing which is a little bit cool is that in Gauss's law, you're used to thinking about sort of integrating something on the boundaries, but here we just get the contribution from the corners, and that's because this is a Lorentzian picture. Okay, so the contribution from the edges are just zero, and I just get this simple relation. Okay. So I can use this fact to determine. I can use this fact to determine I can use this fact to determine x anywhere inside this diamond, right? If I plonk down, if I want to know what is x in here, I just draw any picture that I like. For example, if I draw this picture, then I can determine x in terms of the boundary values here and there. Okay. If I draw it like that, I can determine this x in terms of the boundary values there and there, and so on. Okay. So again, time and space are totally symmetrical here, so you can sort of decide how you want to interpret this fact, but in 1 + 1 dimensions, if you give me the value of x on any two of the boundaries of the causal diamond, I entirely determine what x is inside the space. Okay? All right, so that's fact one about the wave equation. There's another fact about the wave equation we'll need in a second. Another simple and kind of familiar fact. So the following. So let's say that, so it's what I call scrunching. So let's say you have some solution of the wave equation, but you take some 45-degree strips, okay? And there's a solution out here, let me call it x to the right, and some solution here, x to the left of the strips, okay? Then the claim is that from this solution of the wave equation, I can build another solution of the wave equation, of a different wave equation, the same wave equation with a different source, just by scrunching away this region. So what I do is just collapse this region to 0 size. I still just put x right here and x left there. Okay, but now, what do I have to do? I have to include some source, which is just the integral of whatever the source is in the strip as the delta function on this juncture. Okay, now, and why is this true? Well, it's simply if I only care about x to the right and the left, back in this sort of full geometry, I would just draw one of these causal diamonds. Gauss's law tells me x plus x minus x minus x is that total current. And so it doesn't know that it's this finite size thing, right? As far as this is concerned, all I have to do is reproduce the total amount of charge that's in that region that I scrunched away. Okay, so these are two simple facts about the wave equation. You have some complicated solution of the wave equation with some source. You can just scrunch away some region and replace it, and the rest of the wave equation is unaffected. Okay, so okay, is that clear? Okay, those are the only things we're going to need to know about the wave equation. Okay, so now comes the so still nothing too exciting happening. So now comes the idea is that we're going to demand positivity. So we're going to solve the wave equation du dv capital X equals c. But we're going to demand two things. We're going to demand that the source is positive, and we're going to demand that on the time-like boundaries of the space that we're going to look at, on the boundaries x is we're going to demand that c is positive. We're going to demand that x is positive. And that's actually what we're really interested in. Okay, we're interested in characterizing the space of all solutions of the wave equation, which have the property that for positive source it stays positive everywhere inside the sort of domain that we're interested in. So now we're going to talk about asking that this is true in a chunk, and in one of the chunks that we talked about before. Okay, so the kind of simplest thing we're going to do is to ask that this is true. We're going to ask that this is true in a space-time that looks like this. Right? So I'm going to try to solve the wave equation in this space-time. Okay? And you can quickly convince yourself that trying to find these solutions, the solutions to all the x's that have this property, you first have to solve a slightly more restricted problem where x is actually 0 at the boundaries. So it's 0 here and is 0 here. Okay, so I'm demanding that x equals 0 here, x equals 0 here, and then we just want to ask that x is greater than or equal to 0 in there, with the source is greater than or equal to 0. Okay? So that's what we'd like to understand. We'd like to characterize solutions of the wave equation with this property. Note that we can think, again, since this is time, we can think of this as having specified the state on this initial kind of null surface, and I'm evolving forward in time, right? Or I can think about it the other way, because time and space are symmetrical. I can also think that I'm evolving forward in time in this way, but the way I've drawn t, you would think of this as some initial sort of null surface that you defined the data on, and that we're evolving forward in time. So in that way of saying things, what entirely determines the solution of the wave equation inside here is giving us boundary values here. Okay, so let's try to understand why that is just explicitly for a second. So let me put this in here. So I want x greater than or equal to 0 here, and c greater than or equal to 0 here. Okay, but we want to ask, in the space of possible sort of x of u's on this slice, what allowed boundary conditions can I have for x of u such that it's compatible with x staying positive everywhere inside when the sources are positive? Okay? Is it clear the question that we're asking? Sorry? Yeah, with that, so x of u will have to satisfy the boundary condition that it's 0 at this end and 0 at that end, and it satisfies these boundary conditions as we go on forever in both directions. We could have drawn another geometry. I mean, again, this is for any chunk. I could have also drawn something that just looks maybe slightly more familiar. It looks like that. This is another chunk. This is another chunk of the space-time, and it's exactly the same question, right? So now I'm imposing that x equals 0 at this entire top, x equals 0 at the entire bottom, and I want to ask, what constraints do I put on x on this boundary, which has the property that we want? Okay, yes?
Aren't you over determining you should also specifying x0 at the lower point?
No, we're not. And in fact, we can uniquely solve for any x inside by the Gauss law constraint. Okay, so let me just quickly convince you of that. In fact, we're going to come to this in a second. But first of all, you see that given any x on this boundary, I fully specify the x on this boundary, because this Gauss law tells me this plus this minus 0 is that constant, which I know, right? So given the x's here, I fully specify the x's there. Then I'm done. Then I know the x's anywhere. Give me the x's anywhere. If I want to know the x here, this plus this minus that minus 0 is equal to a constant. Okay? And I just determined what that guy is in terms of that guy. So I've fully specified the solution of the wave equation inside, just giving this boundary condition of x on here and these boundary conditions at x equals 0 at the top and the bottom. Okay? But we'll be seeing this quite explicitly in a second. So, all right. So just to say again, we want to see in the space of all functions x of u. These functions x of u look something like, so here's a function x of u. At u equals 0, it has to be 0. U equals 1, it has to be 0. And it has to be positive everywhere there. But I want to know somehow in this space there's some function x of u that's positive everywhere that goes to 0 at the boundaries. Is that function compatible with x being positive everywhere inside or not? So I want to put some constraints on what x of u looks like. Want to figure out what the constraints are on what x of u looks like in order for it to be positive everywhere on the inside. Now, this problem is hard because we are asking some infinite dimensional question, right? In the space of all functions, right? So let's make it a little bit easier. And let's just ask about the values of x at a few select points on the boundary. Okay? So in fact, the simplest thing we can do is just ask, what can we say about x at a single point? So what can I say about x here? So let me call this point, I don't know, A. What can I say about the value of x? Let's call it x1. Okay? What can I say about the value of at x1? Well, let's draw the obvious light cones in this picture, right? So here's x1. So here's some friend on the other side. I don't know, let's call it y1. Okay? And let's write down what the Gauss law condition is. The Gauss law condition says that x1 plus y1 is equal to the integral of the current in there, right? C. Let me just call that C. Okay? All right, so what do I know? I know that I want x1 to be positive, but I also want y1 to be positive, right? At least I want those to be positive. So I want x1 and y1 to be positive with this condition. And so that means that x1 has to lie in this region between 0 and C. Right? So in x1 space, we already learned something interesting, that x1 cannot be arbitrary. It has to lie in this little interval. Okay? On this end, x1 goes to 0. On this end, y1 goes to 0.
So C here is
Okay.
just the fixed.
C's are the fixed. We're imagining that this positive source is fixed. So the only thing that we're varying is the boundary data. Okay? Okay? All right, so that's a little interesting. Let's move on to sampling at 2 points. Okay, so let's say that we sample at 2 points, x1 and x2. Let me draw the light cones. Okay. Now this is slightly more interesting. So I have x1 and y1 and x2 and y2. And this third point here, z, which is on the inside. Okay? And now I want to somehow say something about all of these things being positive, right? So I could literally write down the Gauss law conditions for this mesh, and that mesh, right? That's 3 equations. So let's write them down. So this mesh, it says that x1 plus z minus x2 is some constant, c. This mesh, so let's put some c prime, and c double prime here. This mesh says that x2 plus y1 minus z equals c prime. And this one says that y2 plus z minus y1 is c double prime. Okay? And now note that I want all of these 5 variables, x1, 2, y1, 2, and z, to be positive. My data is x1 and x2. So I want to see in x1, x2 space, there's going to be some nice region where this is true, right? But here are 3 equations that I can use to solve for y1, y2, and z in terms of x1 and x2. Okay? Now I could actually sit here and take linear combinations of these equations to do it, but we can actually go back to the picture and just let the picture do it for us. Let's say I want to solve for z in terms of, I want to solve for everything in terms of x1 and x2, right? Let's solve for z in terms of x1 and x2. Well, that's easy. That's just this equation right away, so we don't have to do anything. So z equals c plus x2 minus x1, and we want this to be positive, right? But let's solve for y1. See, I can solve for y1 just by looking at the Gauss law in this picture. x1 plus y minus 0 equals c plus c prime. Of course, that's a linear combination of 2 of these equations. In this case, it's not so hard to do, to take the linear combinations, but I want you to see that in a second we're going to be drawing more complicated things, that you can just sort of read it off immediately, right? So I want to get the equation for y. So this is also the answer to your question. So we're explicitly seeing how we're solving for everyone in terms of the internal guy. So y1 plus x1 equals c plus c prime. Therefore, y1 equals c plus c prime minus x1. And similarly, y2 plus x2 minus 0 is c prime plus c double prime. So y2 is equal to c prime plus c double prime minus x2. And I want all of these guys to be bigger than 0. And of course, I also want x1 and 2 to be bigger than 0. So let's draw what this space looks like. In x1 and x2 space, so here's x1 and x2. First of all, x1 and x2 have to be positive, so I'm in the upper quadrant, right? But I have to demand that x2 minus x1 is bigger than negative c. Okay? So that means that there is a line coming out like this. And I have to be above this line, right? x2 minus x1 has got to be bigger than negative c. The length of this line is c. But I also have to have that x1 is less than c plus c prime. And now notice how interesting it is that c plus c prime, because the c's are positive, is guaranteed to be further over from where this line started, right? That was not, if I didn't say anything about the signs of the c's, I wouldn't know what this shape looks like. It would depend on whether it cuts it here or here. but I'm telling you the c's are positive. So I know for a fact that x1, which is bounded by c plus c prime, is out here somewhere. So there's a line that's going to look like that, where this point is, so this point is c, this is c plus c prime. And similarly on the other side, I know that y2 has got to be less than c prime plus c double prime. So that's what the picture looks like. Okay. So this is c prime plus c double prime. Okay? And so I have to lie on the inside of this interesting region. What you're going to notice is a pentagon. Okay? Yeah?
Why is that line not lower than the intersection point line?
Because it's bigger than c prime. Because this intersection point is exactly at c prime. Okay? Because, sorry, thank you. This point here is exactly at c prime, because it's a 45-degree line. Right? And so the next one is above that, and so it gets intersected above it. Okay? All right, so you see that already we're getting some kind of cool stuff. That for one point, it had to lie in the inside of an interval. Just for 2 points, it has to lie inside this pentagon. And if you remember from last time, the interval was the one-dimensional associahedron, and the pentagon is the two-dimensional associahedron. And let's keep going. So what if we have 3 points on the boundary? Okay, if I won't write down all the equations, but we'll just do some counting. So if I have 3 points on the boundary, so I have x1, x2, x3, and then I have how many other points? 1, 2, 3, 4, 5, 6 other points. So I have a total of 9 variables. How many mesh relations do I have? 1, 2, 3, 4, 5, 6 mesh relations. And so we're going to get a 3-dimensional polytope. So it's manifested as a polytope. I hope that's clear, right? It's manifest. We're just cutting things out with the inequalities. So we're going to get a 3D polytope with 9 faces, which are associated with these demanding the positivity of all those variables. Just like here, we got 5 faces because we demanded the positivity of all 5 variables. So we got, okay? And you can just, if any of you have Mathematica open, you can just like plonk down these equations right now. Just do region plot 3D of all the equations, and you'll get a beautiful picture of a 3-dimensional associahedron. Okay? So these guys are associahedra in general. The x's have got to lie inside an associahedron. So in this case, the associahedron is this answer to this extremely simple question. But again, the word positivity was important, right? So we had to ask for positive solutions of the wave equation. But positive solutions of the wave equation in kinematic space force the x's to lie inside an associahedron. And so this is a very particular realization of an associahedron. It's not just some random combinatorial associahedron. It's a very particular way of cutting out the associahedron with linear equations that's associated with the wave equation in this way. But instead of going through the example and showing that it's the associahedron, I now actually want to prove that it's an associahedron. In other words, what I want to now show is why this picture does what we set out to do. This picture makes it obvious that we have objects that are polytopal. That's clear, again, just by construction. We're asking, once we sample at finitely many points, we're manifestly talking about the interior of some region that's cut out by a bunch of linear equations. Okay? So it's going to be manifestly polytopal. And now comes the magical part. It's going to manifestly factorize on its boundaries. Okay? So I want to show you how we see both the polytopality and factorization. Okay. Okay, so let me now explain why we have factorization. And let me again just go back to this continuum picture. Draw this a little bigger. Okay. Now, I'm interested in solutions of the wave equation which stay positive everywhere inside, right? So what does it mean to go to a boundary of this space? What it means to go to a boundary is to put x 0 somewhere inside. All right, so let's say I put x 0 here. What I'm now interested in doing is figuring out what does the space look like that's compatible with x equals 0 there. And what I'm shortly going to show you is that the space is a direct product of two triangles that look like exactly the same thing. Okay? But let's see how that emerges. Well, the first natural question to ask is, if I put x to 0 here, where else can I put x to 0? Right? And what I'm about to show is the key point of this entire story, and it's basically one extremely simple fact. We'll talk about it in a few ways. But the point is that if I put x equals 0 there, then there's this entire region. If I draw the natural light cones in this way, I cannot put x equals 0 in any of these other places. Okay? In other words, said another way, if I put x equals 0 here, all the points that are time-like separated from this one, either in the future or in the past, but which are causally connected to this one, so that there is a causal diamond that has this one on one end and the other one on the other, none of those points can go to 0. In other words, if I put, so let me say the more general statement. If you draw any causal diamond that fits in the space-time, any causal diamond at all, if I put x equals 0 here on one corner of the diamond, remember this is time, if I put x equals 0 in the past, I cannot put x equals 0 in the future. Why not? Because, remember, if this is A, B, C, D, I have to have A plus B minus C minus D is something positive, because I assume that the current is positive. And so if I put A to 0 and B to 0, I get a contradiction. The sum of two negative things is positive. Okay? So that's the sort of key point here, that causality, whether or not you have points that are causally connected in the sense that, if you think of these as observers, that the future observer is in the causal, well, is that the past and the future observer are part of a causal diamond in the space-time. If one of them goes to 0, the other one cannot go to a 0. Okay? Yeah, it's 0 at the top and the bottom. Okay, we're forcing it to be 0 at the top, but the bottom, if we put a 0 here, you can't put it to 0 anywhere in here, right? All of these things, there's someone who fits up to that point, right? And now, but you can put it to 0 there, here, or there, or there. Okay? Furthermore, so I can't put x equal to 0 anywhere in this shaded region. But furthermore, I don't care about the, yes? Yes. Sorry? Well, this is some charge density here. So x is 0 at the top, and x is 0 at the bottom.
So the triangle that has two vertices over there, one is 0. So the middle one,
Which triangle are you talking about? Like this one?
The one with two vertices on the.
This one?
The one next to it.
What are you talking? Sorry, this one?
Yeah,
Yes.
Yeah. So it has everything 0. So the charge inside should be 0.
No, the charge inside does not have the charge inside does not have to be. Yeah, because that's not a causal diamond in the space-time. Okay, so we don't have an equation for that guy, right? Okay, so it has to be an equation that involves this plus this minus that minus that. We don't have that equation. Any other questions? Okay, all right. So, but notice that everything about what's inside these shaded regions I can reconstruct just by knowledge of boundary values, for example, here. So not only can't I set anything to 0 there, but everything, if I want to know what the x's are in there, I can reconstruct them by knowing what these boundary values are. Therefore, as far as the kind of degrees of freedom that I actually have, the degrees of freedom that I actually have involve the x's here and the x's there, because I can certainly reconstruct all the degrees of freedom in there just from all the other boundary values that I have. Okay. And by scrunching, this is exactly the same as the following picture. So I'm now just going to scrunch away this region and that region. And what is the new picture that I get? The new picture that I get is a triangle, top of another triangle. I have to, of course, add some delta function positive source on this bottom triangle to like make up for the sources that are there. So I add some extra source there. Okay. But that's now what I get after I scrunch away those regions. And this point here is a point that I set to 0. Okay, so what do we conclude? We conclude that all the solutions of the wave equations that are positive for this problem, when I set x to 0, are exactly the same as the solutions are completely determined by the solutions of the wave equation for this problem, where I set x equal to 0 here as well as x equal to 0 there. But this is just a direct product of two triangles. Okay. Okay. So we see factorization and therefore, it's completely manifest that once I sample this guy at finitely many points, I get a finite polytope, but the finite polytope has a property that on the boundary it factorizes into lower polytopes of exactly the same type. Okay, okay, so yeah.
I'm missing the scrunching bit. So you're ignoring the moment.
Well, there's no momenta here, right? So what I'm saying is that I'm trying to characterize all of the x's here, which all the x's here that are compatible with the condition that it's positive everywhere and 0 there. I'm telling you that all of those x's are in one-to-one correspondence with all the x's that satisfy exactly the same rules on this picture. So, and that is exactly one problem and another problem. Okay? And it factorizes. It literally factorizes. Now, of course, there are more variables here. So there's some concrete formula. If you want to know what all the x's are here, they're entirely determined by giving the x's here and the x's here. Okay, so if you give me, because this boundary is nothing other than this part plus that part. Okay? So if you give me all the data on this part and all the data on that part, you've given me all the data here and there from which I can reconstruct everything. Okay, so I'm giving you a sort of a map between this problem and this one. And that just tells you that everything here on this boundary looks like the direct product of two lower problems of the same sort. Okay? Okay, so this is really the sort of key conceptual point, is that causal dependence in this 1+1 dimensional space-time, this auxiliary 1+1 dimensional space-time, which is how we're interpreting kinematical space. So this has nothing to do with ordinary space-time. This is some funny auxiliary 1+1 dimensional space-time that how we're interpreting kinematical space. That causality in this 1 + 1 dimensional kinematic space tells you a notion of whether two events are compatible or not. Two events are compatible or incompatible if they fit on corners of a causal diamond. They're compatible if they don't. Okay? And compatibility or incompatibility from this causality point of view maps precisely in the mapping that takes a point inside here to the chord of a polygon. It maps precisely to whether chords cross or don't cross. So that's the entire little point here, is that there's a mapping between causal diamonds in this 1 + 1 dimensional picture and just the simple question of whether chords cross or don't cross in the identification. If you like, all we've done in this entire lecture is when we draw that picture of the polygon and we say, oh, the chords are associated with xij, it's so easy to do, we do it right away, but we kind of in our mind see a one-dimensional picture just of the polygon. But if we really want to see all the variables, we have to draw a two-dimensional picture. That's what we did, and we made a map between the sort of two-dimensional picture of the variables. We drew we just characterized the space of the two-dimensional picture of the variables. But now we can ask, in that picture, what does whether chords cross or not cross look like? And if chords cross, it means that the points are inside a causal diamond that fits in this space-time. If they don't cross, it means that they're not. Okay? And just that primitive fact then tied with this simple picture of the wave equation gives us both manifestly an object that's polytopal and that factorizes on the boundary. Okay? Yeah?
Just something that's like conceptually cleaner about this one is that you've taken the limit as the number of particles goes through.
That's right, yeah.
So it just factorizes into two copies of itself.
Yes.
Is there an analog for the amplitude?
Well, the amplitude also the tree-level amplitude also factorizes into two copies of itself, but there's a lot more going on. There's k. There are different kinds of boundaries. So on different boundaries, it factorizes in two copies of itself into different k and so on. Right.
But it's perfectly fine
Right.
to take the limit as the number of particles.
Yes, you can also perfectly well take the limit as the number of particles goes to infinity for the amplituhedron. But here, yeah, that's right. Yeah, you can do the yeah. Okay. So now what are we doing for a fixed number of particles? So finally, this is the geometry. So just to emphasize again, what we're doing. So let's say I do this. I look at this chunk again. So this is 1, 2, then 1, 3, 1, 4, up to 1n at the bottom, and so on. Right. So we fill in this mesh. Then I'm asking for all the xij to be positive. I'm asking for the x's to satisfy the wave equation. Now, the wave equation is the statement that I can associate with any ij here. So with some ij, the wave equation just says like xij plus xi plus 1 j plus 1 minus xij plus 1 minus xij I plus 1j equals Cij. Okay, so I'm associated with a given point inside here. I'm going to just call that source in here Cij. Okay, and so you see that the number of these C's is smaller than the number of X's, precisely because all the X's I'm associating a mesh with every variable, right? I'm associating a mesh to the right of every variable, except there's no right to the variables right at the end. Okay, so I have precisely nn minus 3 over 2 minus n minus 3 of the Cij's, just the ones that I see in this, mesh. Okay, and the claim is that these equations cut out the associahedron. The n minus 3 dimensional associahedron. And I've given you the sort of conceptual reason for it, because they clearly cut out a polytope, and the polytope manifestly factorizes on its boundaries. Okay, so it's some polytope that manifestly factorizes on its boundaries. Yes?
I just want to go back to the factorization. I was
Yes.
wondering, is it possible the regions that you scrunched, could they have zero charge exclusively, and the rest could have a positive?
Doesn't matter. Yeah, it doesn't matter.
Like
No, that's right. It doesn't matter. That's right. It does not matter. Okay, so this is yeah.
Would that imply like some of the chords then would be, I guess they would be zero as well, right? Like in the original.
No, they don't have to be zero. I mean, yeah. So if you literally send the charge, in fact, let me just interpret this in a second. If you send some of theseCij's to zero, then it's possible to kind of shrink the edges and maybe even some of the faces of this polytope. Yes, you can certainly do that. Yeah. Yeah. So if you want to see the kind of generic behavior of the polytope, you want all these C's to be positive. Okay. Yeah. Well, then first of all, none of it would work. But the ultimate sort of combinatorial fact is, the very simple fact is what I told you. If you plot Xij's in this two-dimensional mesh, Euclidean, Lorentzian, you don't care, it's just some two-dimensional mesh. Even if you draw it right side up so it doesn't look like light cones, draw it however you like. The invariant fact is that two chords crossing corresponds to 2 points on opposite sides of a diamond. Okay? And that's what brings causality to life. Okay? Because you want to have something care about whether the causal diamond does or doesn't fit inside the space-time. The ordinary wave equation cares about causal diamonds. The Laplace equation does not. Okay? So that is the only reason. Okay. Okay, but now let me say, so this is the geometry. So if I kind of okay, so now my kinematic space is X space. In X space, I have a positive region that I won't even draw in a curvy way because it's not curvy. I have a positive region which is just where all the x's are positive. So it's like a simplex, right? So this is P. Okay? But I have found in kinematic space, I have found a subspace. What is the subspace? The subspace is the solution of the wave equation. Okay? So here is a subspace. S. Right? And the subspace intersects the positive part. So remember, this P is just where all the Xij's are positive. The subspace solves wave equation. Okay. Sorry? The subspace is labeled, the subspace has some positivity constraints on it. The C's have to be positive, okay? So there's a subspace with some positivity condition, but for any C that you choose that's positive, I get a subspace. The subspace intersects the positive part in a positive geometry. In this case, it's just a polytope. It's the associahedron. Okay? And now what is the amplitude? The amplitude is an n minus, so this is an n minus 3-dimensional subspace. The kinematic space is nn minus 3 over 2 dimensional. And so the scattering amplitude is an n minus 3 form with the property that when you pull it back to the subspace, you get the canonical form of the associahedron. So this story is, I hope you see, qualitatively identical, but much more straightforward than the story we saw for the amplitahedron. Okay? Everything is polytopal. Now, but the amplitude is thought of as a differential form on this whole space. But when you pull it back to this subspace, you strip off the overall volume form on the subspace, all those relative signs become plus signs, and you literally get the amplitude. Okay, so that's how the amplitude is recovered as well.
What would we see? The subspace depends on
Yes,
Z, right?
the subspace depends on Z. So in the analogy with the amplitahedron, here we have the space of all x's. In the amplitahedron, we had momentum twister space. Here, in the amplitahedron, the positive part was this fancy thing where all the I plus 1, JJ plus 1s wound around the same way, and there was some net winding number. Okay, so it has positivity and some topological thing on top of it. But remember, it's not dissimilar. All the II plus 1, JJ plus 1s positive, or just the poles are positive, right? That's all the poles are positive. It just needed this extra topological information too about the actual winding number. Here, it's simpler. Just the poles are positive. Okay? In the amplitahedron, you have to find a subspace that was 4K dimensional, that was this linear subspace where you took some initial Z star, and then you translate in some direction delta. That gives you a 4K plane. And we have to ask that Z star and delta gave us a positive matrix. We thought of that Z star and delta as the external data of the usual Y space picture of the amplitahedron. Here, it's the C's. So you give me positive C's, they specify some hyperplane. In both cases, when that hyperplane intersects the positive region, we get a positive geometry. In the amplitahedron case, the positive geometry is the amplitahedron. In this case, the positive geometry is the associahedron. Okay? In both cases, the scattering amplitude is the canonical form that lives on the whole space. When you pull it back to the subspace, it gives you it's some form, lower form that lives on the whole space, that when you pull back to the subspace gives you the canonical form for the positive geometry. In this case, the canonical form is just the canonical form of the associahedron. And actually, this is the last thing that I want to mention. Associahedra are examples of things called simple polytopes. A simple polytope is one which has the property that at every vertex, if it's an n-dimensional polytope, there's only n faces that meet at a vertex. Okay, so that means that locally in the neighborhood of every vertex, it looks like a simplex. Okay, so for example, obviously a tetrahedron is a simple polytope, but a square pyramid is not. Okay, because there are some locally, the top vertex, it seems like there's 4 faces meeting on it, not 3. Okay, now there's a very simple for simple polytopes. For simple polytopes, there's a very simple formula for the canonical form for the polytope. The canonical form is just the sum over all the vertices of the d log of all of the linear equations, of all the linear equations that are associated with the faces that meet on V. Okay, so I think we had talked about this. And with the overall sign given by the orientation, in an obvious way by the orientation of the of that simplex locally around the vertex V. One simple way of understanding this formula is if the remember, for polytopes the canonical form is also the volume of the dual. Okay. And if the polytope is simple, that means that at every vertex you have, like it's a 3-dimensional polytope. At every vertex there's 3 faces meeting. What does it mean in the dual? That means that the dual is what's called simplicial. That means that in the dual polytope, all the vertices become faces. That means that every face looks like a triangle. Every face is bounded by exactly, every face looks like a triangle. So if the polytope is simple, the dual polytope is simplicial. The faces don't look complicated. Every face just looks like a triangle. And therefore, there's a very simple way to compute the volume if every face looks like a triangle. Just put a point on the inside, draw a tetrahedron out to all of the triangles, and add them all up. Okay, so that's why there's obviously a formula that just sums over all the faces of the dual polytope. And that formula, interpreted back in terms of the original one, is just taking the wedge of the d log of all of the linear variables that vanish on the faces that touch a vertex. So when you have a simple polytope, this is a simple way of getting the canonical form for it. Okay? Now, what are the vertices of this associahedron? The vertices of the associahedron are just when you set as many x's as you can to 0. But we know what all those are. Setting as many x's as you can to 0 are exactly triangulations of the polygon. That tells us that it's exactly simple, because I can't set more than n minus 3 of them to 0. So we see that the associahedron is a simple polytope. And we see that every vertex of the associahedron is associated with a triangulation of the polygon, or dually a Feynman diagram. So I just told you that it's an associahedron, but now I've proven to you that it's an associahedron in detail, right? Just by seeing that we can label every one of the facets exactly by some chain of these x's that go to 0 that end up at a vertex, giving me what look like Feynman diagrams. Therefore, one formula for the canonical form of the associahedron is the sum over Feynman diagrams. So that's one very, very nice thing about this story, which is easier than in the case of the amplituhedron, is that we can see very easily the connection to Feynman diagrams. Okay? So Feynman diagrams represent one triangulation of the associahedron, sort of one of the easy ones, which you can associate with any old simple polytope, just taking the wedge of the d log of the variables associated with every vertex. Okay? So we discover an associahedron in kinematic space. We discover an associahedron in kinematic space. But and from there, one simple formula for the canonical form is just Feynman diagrams. However, we know something. We know that Feynman diagrams are hiding a fact. They're hiding that this form has no pole at infinity. Now, it's obvious this polytope has no form at infinity because it only has singularities on the boundaries of the associahedron. However, term by term, that's invisible. Okay? And that's related to the fact that this form is projectively invariant. This form that lives on the big space is projectively invariant, but that's not obvious term by term in the Feynman diagrams. Okay? So that's, again, we've said this a couple of times, but we're seeing it in more detail now. The object, this is an intrinsic definition of what the object is. It has various, we see the polytopal nature of the combinatorics. We see factorization. We see this hidden projective invariance, all as the features just sort of built into the problem. We also see Feynman diagrams as one quite nice way of triangulating the answer, which, however, breaks some of the obvious symmetries. Okay? So it doesn't manifest this hidden projective invariance. And this hidden projective invariance is literally a prediction about the amplitude, which is non-obvious. And the prediction is that if you take the amplitude, you pull back to one of these subspaces. So you literally have a function of x's and these c's. The prediction is that if you hold these funny c's fixed and you send the x's to infinity, it goes to 0 faster than you would naively think from each Feynman diagram alone. Okay, that's literally the absence of a pole at infinity. Just like in BCFW, right? Just like in BCFW, when we went off to infinity, naively it went with some power law, but in fact it went faster to 0 faster than that. Okay, so it's a very specific prediction, which is not true of any diagram term by term, and it's not true of any sum of a subset of diagrams. It's only the sum of all of them together, which has this sort of remarkable feature that it vanishes faster at infinity than you would naively predict from any one of the terms. So this is the sort of hidden symmetry that I've alluded to many times that we see even in this simple biadjoint theory. Okay, now let me just almost out of time, but let me say a couple of things. First, something we probably won't have time to talk about, but since you actually brought up, the person is gone, but since this question was asked already, it is natural to ask what happens when you take these C's and you sort of shut them off, right? So it's actually especially natural to ask what happens when you obviously if we shut off all the C's, we shrink the entire polytope to 0, right? But it's sort of natural to ask what happens when you turn on one C at a time. turn on one C, another C, another C, another C, okay? If I shut off all but one of the C's, I get a much simpler polytope. In fact, it's not even generically top dimensional. If we take some of these simple examples, like the pentagon, let's say you take the pentagon. I'll just tell you what the answer ends up being. If you take the sort of pentagon case, and you shut off C and C prime, I forget which ones I called them, but if you shut off two of them, what you'll be left with is an interval. If you shut off another two, what you'll be left with is another interval, and the last set actually gives you something that looks like a triangle. Okay, so in these limits, when you shut off all but one of the C's, you get very simple objects. And there's then a very pretty interpretation for what the whole polytope is. There's a notion of a Minkowski sum of two polytopes. It's the most trivial thing you can imagine a sum could be. If you have a space A and B, the Minkowski sum of A and B, if the vectors in A are V and the vectors in B are W, they're just all V plus W's. Okay? It's a set of all V plus W's, so V in A and W in B. But if you take the Minkowski sum of, so if the variable that's left here is C1, C2, and C3, the Minkowski sum of C1 times this plus C2 times that plus C3 times that gives you the entire polytope. Okay? So basically by definition. So I got the polytope by shrinking some of the C's, and I'm just adding them back. So this is interesting, that we're not just getting the associahedron in some random realization. We're getting the associahedron naturally. Each mesh, each little piece of the mesh is giving us some little building block of the associahedron. Each little mesh is giving us some little building block. And if I take the Minkowski sum of the building blocks that I get from all the meshes, then I get the entire associahedron. All right, now, I might allude to this at the very end of the next lecture, but this is a very natural fact about this way of building up the associahedron, and that fact is a hop, skip, and a jump from string theory. Okay? So string amplitudes, the famous Kobe-Nielsen formula, the beginning of string theory, from the beta function to the sort of general endpoint formula of the Kobe-Nielsen amplitude, has a direct interpretation. You've never heard of strings, you've never heard of anything else, you're just playing this game, and you want to find a way to write this canonical form. Well, there's a general strategy for writing canonical forms of any polytope, associahedron, any polytope at all, which involves certain integrals. It has nothing to do with string theory. It works for any old polytope, right? It involves certain integrals. In fact, these integrals were written down in various guises by mathematicians decades ago. It's nothing to do with strings or a worldsheet or anything. But you write down certain integrals, and these integrals give you, naturally, the canonical forms for polytopes, especially naturally when the polytopes are presented as a Minkowski sum. So if you have a set of polytopes that are naturally given to you as a Minkowski sum, and you shove it into this machine, you'll get some object that will depend on a parameter alpha prime. And that ends up being the string amplitude. So there's a kind of a very direct way, without any mention of a worldsheet, to go from this picture of the associahedron in kinematic space to string amplitude. So I probably won't have too much time to talk about that, but I might say a little something about it. But now I want to say something else that we will talk about next time. So here we just sort of talked about the solution of the wave equation as a global thing. We sort of, plonked it down, and we found what it looks like, and it factorizes, and so on. Well, there's a very natural question that you could ask. How can I solve? I mean, here we gave various. We solve these mesh relations in various ways to determine all the x's on the inside, given these x's on the boundary. But there's a very natural question to a physicist. How do we do this gradually in steps? In other words, I want to determine all the x's on the inside by time evolution, right? I want to imagine this is some initial surface, and then from this initial data, I'm next going to determine what that point is. So that's my first step in the time evolution. The next step in my time evolution will be I'm going to determine what that point is. The next step, I'll determine what that point is, and so on. Then I get to this one. Now I have a new surface. Now I'll determine what that one is, and so on. Okay? So we're going to talk about what a natural picture of just evolving in time is, one step at a time. Okay? It's a very natural thing to ask. And as we'll see, asking that question motivates drawing a certain quiver associated with this diagram. Okay, we're going to draw a certain quiver associated with this diagram. And the rule of time evolution will end up being an extremely simple one at the level of the quiver. It's flipping a bunch of arrows of a certain type on sources or sinks. So that is going to give us a rule for starting from a quiver and walking just by everywhere we see sources, or let's say we decide they're sources. Everywhere we see sources, we flip the arrows on the sources. We solve for a new variable associated with that node by the mesh relations, by the wave equation, and we keep on going. Okay? So this won't, if it's not obvious to you, we'll see it next time. But we're going to start next time with trying to interpret the solution to this wave equation as time evolution. When we interpret it as time evolution, we'll abstract that away, just so you have an idea where we're going. You know, this picture, the fact that they're all on a null cone is going to be on a null line, is going to be represented by the following quiver. The fact that they're all 45-degree lines in one direction is the fact that all the arrows are oriented like that. But at the next step in the time evolution, you see I can solve for this variable. Given everything that I had here, I can solve for this variable first next. And so this now looks exactly the same, except at the end, I'm flipping to go the other way. So at the next step, we're going to have a quiver that looks exactly the same. But at the end, that arrow will be reversed. Okay, and so on. Okay, so we're going to have a picture of time evolution. And we'll start with a bunch of variables, x1, x2, blah, blah, xn minus 3. And we're going to have some new variable here, some x prime. So I change one variable to another, reversing the direction of all the arrows, and with a very simple formula from the mesh equation that tells me what the new x is in terms of the old one. Okay? So we'll just sort of practice interpreting time evolution in this diamond in this slightly more abstract way in terms of starting with a quiver and mutating, which means going to a source that's only a sink and flipping the direction of the arrows, and writing down a new variable at that node with a simple rule and continuing. Okay? In the case of these linear quivers, we're just going to reproduce what we saw with the wave equation. But you can then abstract this rule away to a general quiver. Okay? If you abstract this rule away to a general quiver, something miraculous happens. If you do it for a totally arbitrary quiver, you find that while in this case, the process sort of ended in a natural place, and the polytope sort of closes up, and we get this finite object. Then if you do it for a totally random quiver, the process never ends. The polytope never closes up, and it just is some infinite crappy thing. But for very, very special quivers, it ends up giving you a finite polytope. Those special quivers are associated with Dynkin diagrams. The quivers are nothing but orientations of Dynkin diagrams. This is a miraculous fact. The fact that Dynkin diagrams show up as the answer to this question, finding these sort of quiver-like generalizations of associahedra is not obviously related to the classification of Lie groups question. Okay, so the fact that Dynkin diagrams make a second appearance here is quite remarkable, but is not coincidental. And the objects that we're going to define in this way are actually the polytopes associated with the cluster algebras, even though I won't have told you what a cluster algebra is. Okay? But we'll have done a lot of the stuff about cluster algebras without actually telling you what a cluster algebra is. Okay? And in particular, it's known that cluster algebras are finite precisely when they're associated with quivers that are Dynkin. Okay? So this sort of the fact that Dynkin appears in both cases is something that you can actually see from this much more pedestrian point of view. Okay? Having seen all of that, there is something else that we will abstract away. I'm just giving you just a sort of teaser so that some of you show up on Thursday, even though you have exams and stuff like that. So that in this case, when it's a chain, all this business with the wave equation and factorization and all this sort of beautiful stuff, it's abstracted away to a very simple thing. Forget even about the orientations. You have a Dinkin diagram that looks like this, just AN for this case, and the way it factorizes is simply that you remove a node. So that's why it factorizes into two smaller Dinkin diagrams of exactly the same type. Okay, so that's why AN factorizes into AN cross AN, AN1 cross AN2. That's exactly the kind of factorization that we expect for tree amplitudes. Okay? But of course, this ends up being exactly the story in general. So if we look at the other classical type Dinkin diagrams, let's say for B and C, we have Dinkin diagrams that look like this. So if I call this B, how should B factorize? B should factorize if I remove a node into, on one side it looks like an A, but on the other side it still looks like a B. Now, what kind of amplitudes have this property? That their amplitude of something factorizes into itself times something that looked like an A, which was just like phi cubed, planar phi cubed amplitudes. These are exactly amplitudes where you imagine you have some sort of colored particles, but also they emit a graviton, or a dilaton, or something that's uncolored, so it can go everywhere. So let's say you look at all amplitudes of that form, then how does this factorize? Well, however you factorize, the guy that's emitted is on one side, and it's not on the other. So therefore, it has to look like the boundary equals B times A. What about the final classical type, which is Dn? So the Dn Dinkin diagram looks like this. And so what do we get for the boundary of D? Well, once again, if I remove one of the nodes here, the boundary of D looks like D cross A. But there's one other kind. I can remove this guy. This is just another A. Right? Now, where have we seen this kind of factorization before? This is one loop. Because at one loop, you can have one loop diagrams that factorize into a loop times tree on one side. That's the D cross A. Or we have our friend, the forward limit terms, where I just take this leg and I open it up. I cut the internal propagator. Then I just get a tree, a different tree with two more legs. And that's exactly the second kind of factorization. Okay, so, and this is going to allow us to attach polytopes, just like we have for phi cube theory. First, it captures all the combinatorics of the Feynman diagrams, but also the canonical form of the polytope, exactly the same story, actually computes the amplitude, okay? At least the integrand for the amplitude. And that will happen for these generalizations of the associahedron for these classical cluster polytopes for B, C, and D type. Okay? So all of that we'll be able to sort of understand simply by kind of following our nose. There is this sort of step of abstraction to, it's very, very natural to think about this time evolution. I didn't mention that there, even as you time evolve along, there's a notion of entropy that we'll discover. As you time evolve along, there's a certain quantity that monotonically increases. And it's important to keep track of this monotonically increasing quantity as we go along, which tells us where to stop. Okay, but anyway, you have this idea of time evolution more abstractly associated with the quiver. See, in this picture, you know where to stop. If I just tell you to do this some rule on quivers and mutate on sources or sinks, you could, in principle, just keep going forever. So something's got to tell you where to stop. And there is a natural notion. There's some monotonically increasing quantity that hits a maximum value, then you have to stop when it hits that maximum value. So that takes some inspiration to kind of think that you're supposed to abstract that away from this picture. But once you abstract that away from this picture, you can ask exactly the same questions for any quiver, and in this way discover a lot of the non-trivial polytopal juice of all of these finite type cluster algebras. And the classical ones are attached to scattering amplitudes in exactly the same way as the associahedron is attached to phi cubed tree amplitudes. What is the E8 polytope? Who knows, right? What physics interpretation does it have? Who knows? That we don't know. Okay, so It's obviously something that doesn't make sense for arbitrarily large n. And the last thing I will say, which we won't talk about next time because probably we won't even really get to talk about the string amplitudes next time, but just as I told you that this picture of the polytope as a Minkowski sum immediately suggests a string amplitude, so there's an analog of a string amplitude associated with all these other cluster algebras as well. They have all the usual magical properties of string amplitudes. They're exponentially soft. They have Regge behavior. They have channel duality. They have all these facts that string amplitudes have with no worldsheet in sight. Okay? So they're not canonical string amplitudes in any way. So I think it's an interesting question to figure out if they have any purpose in life. And of course, as alpha prime goes to 0 in all these classical type cases, they reduce to field theory amplitudes in a way very, very analogous to ordinary string amplitudes. Anyway, that's our plan for next time. There's a bunch of ancillary things. I'm just telling you many facts. But our plan for next time is to slowly go back to this picture, think about it in terms of time evolution, abstract it away to these quivers, so I can tell you something about general cluster algebras, and make the claim about amplitudes through to one loop. Okay. Yes.
Is there any physical meaning associated with these diagrams?
Is there not yet? Well, I mean, there are many connections. So there's a connection between the simple roots of the Lie algebra and the normal facets of these polytopes, for example. Okay, so there are lots of connections, but there's no obvious sort of purpose in life to the. There is actually for AN there is for AN there is because there's naturally a Lie algebra. There's a Lie structure associated with the moduli space of endpoints on P1, and that's not unrelated to the fact that the associahedron has an AN. But the meaning of for B, C, D, and the other ones, yeah, there's no obvious, at least not obviously to me at the moment. And as I said, the fact that this is of course a very famous fact in math. I'm not adding any. This is not a surprising news. I mean, it's an amazing thing, but it's been well appreciated for decades. It's very mysterious that Dynkin diagrams show up as the answer to very seemingly really radically different questions. So it's not like I mean the question that you pursue here in order to figure out that the objects you have finite polytopes by this funny construction looks absolutely nothing like, Dynkin's original question about the classification of Lie groups at all. So it's kind of very surprising that Dynkin diagrams keep showing up. There's kind of I know of kind of three different kinds of questions where Dynkin diagrams show up as the answer, and it's not obvious, certainly not obvious to me. And I've talked to a few mathematicians who are sort of obsessed with this question, and at least according to them, it's not really conceptually obvious to them why it keeps showing up. So that's why, precisely because it's not obviously the same question, there's no obvious correspondence between the Lie theoretic aspects of the Dynkin diagram and the polytopal ones, other than some correspondence, as I said, between the normal vectors of the polytopes and the root system. Yes.
So very naively, we were able to reconstruct the associahedron or the
Right.
planar phi cube
Right.
amplitude using a differential equation on the Kinematic space.
Right.
I'm curious if there are differential equations associated with the theories that correspond to that.
Very much so. Very much so. And it's kind of obvious what they're going to be, right? If you think about this AN kind of as like a discretization of this, what should the other ones be? The other ones, the N, is basically the same for everyone, right? So as you make N big, the only difference between A, B, C, and D is just at one end, right? So, I mean, what the Dynkin diagram looks like is just a long chain, either a little antenna at the end, or with a little two arrows at the end, or with nothing at the end. So what are the spacetimes? They're a strip. They're a strip with a boundary condition at the top. It's like you put a brain at the top, or you do a folding. All right, and that's it. So we play with these 1 + 1 dimensional spaces. We do these few things, and we discover B, C, and D, like that.
And the equation that you used to
The wave equation. It's the wave equation. It's the wave equation with, but you have to be careful about what the boundary conditions are. So now when we put boundary, we have to think about what the boundary conditions are. And then So that's a very poor man's way of discovering all these things, even without any of this quiver nonsense, okay? You see there's something cool about the wave equation, great. You want to play with the wave equation. Now you want to say it's a strip, but now there's something at the top, okay? I want to put some degrees of freedom at the top, like some extra particle at the top. Good. So I put it there, but now I have to write an equation for that guy at the top. And now I'm guided by something. And the guide is something that happened automatically and was magical, but it happened automatically, but which I stressed, which is that the shape that you got did not depend on these C's, right? They're all positive, and the positivity guaranteed that the kind of new wall that you put in, you never had to worry about whether it would cut a wall in front or behind of a wall you had before. So you could call this property sort of C independence, or sort of shape independence, that the independence of the polytope on the parameters. If you ask that the equations that you write down preserve this property, it turns out to be almost impossible to do. And you get roped into very, very specific kinds of boundary conditions to put, let's say, at the top of the strip. Those boundary conditions turn out to be Dn. Okay? If you now take the strip and instead just fold it in half, demand some symmetry around some plane and fold it in half, then that gives you, again, something else. That turns out to be the B and the C types. Of course, from here, you won't discover E8, E6, F4. Those are not in the large N limit. That they have no good continuum description. So there is something conceptually more correct about starting from these quivers. So that really tells you everything. But if you just want to think that there are some, but they're not obviously connected to amplitude. So if you want to think that you're asking questions in kinematic space, then the kinematic space gets sort of further. You put some strips, you make some identifications, you play, and you find the other examples. Okay. Yeah. No. That's an excellent question. What is the interpretation of the differential forms in this case? They're not fermionic variables. It's just here they're just here they are. Yeah, it's a completely bosonic theory. But what I can tell you, there's something kind of there is some interpretation of them, but it's a rather remarkable interpretation, which you don't see the full force of until you consider not just one ordering but all orderings, the completely non-planar theory. Okay, so here's the interesting fact. So let's say you imagine drawing any cubic diagram, tree diagram. Of course, any tree diagram can be made planar some way, but I don't know anything about the ordering of the legs, right? This might be 1, 6, 4, 3, 2, 5, right? So, okay. Now, with any cubic diagram, if you're computing in the full phi cube theory, this bi-adjoint phi cube theory, if you weren't doing the color trace decomposition, with any diagram, you would just associate a bunch of FABC factors, right? So associated with every diagram is naturally some color factor, given just by multiplying FABCs on all the vertices. Okay, so with any diagram gamma, there's some color factor as C gamma, okay, which is just given by FFF. Okay. But there's another thing you can associate with a given diagram. You can associate with a given diagram gamma, there's a certain form, omega sub gamma, that you can just think of as the product of the dS's, the d of the propagators that occur. I'm not even using the x variables anymore because it's not just one ordering. I have all orderings. Okay, so it's not even convenient to use the x's anymore. I'm just going to use the s's in one. Okay. So also associated with gamma is something else as a differential form, which is the product of the. So this is the product of the f. This is the product of the d log s's. You see, these are kind of dual. They use dual information. C involves the vertices of the graph. Omega involves the edges of the graph. Okay? Now, the C's satisfy Jacobi relations. because they're color factors. And in particular, the easiest way to think about the Jacobi relations is as relating three graphs to each other, where out here, who knows what's happening to the rest of the graph. But inside, you look at this plus this plus the cross equals 0. Okay? So that's exactly what the Jacobi relation says, because it says whatever else is happening outside, FF plus FF plus FF is equal to 0. Okay? So it's a statement about C gamma S plus C gamma T plus C gamma U is equal to 0. Okay? The remarkable claim is that the omegas satisfy exactly the same identity. So something made out of kinematic invariance satisfies precisely color Jacobi relations. And the reason for this is really simple, is the thing that you learn early on in field theory. When you think about, just kinematics, if you have P1, P2, P3, P4, you learn that S plus T plus U, S plus T plus U, is actually the sum of the masses. So it's P1 squared plus P2 squared plus P3 squared plus P4 squared. But this means that ds plus dt plus du is the d of all of these things. And therefore, if you wedge ds plus dt plus du into the dp1 squared, dp2 squared, dp3 squared, dp4 squared, which is what you do if this went out to the rest of the diagram, you get 0. Okay, so this sort of basic fact, this basic 7-term relation, actually explains that color factors satisfy that kinematic these kinematic forms satisfy exactly the same algebra as color factors. And so, in fact, we can interpret these forms as actually giving us color information. So it's kind of fascinating that you can think about, for example, in Yang-Mills theory, you can think of that the Yang-Mills amplitude is actually a differential form on kinematic space, directly a differential form on kinematic space. Of course, it has some polarization vectors and momenta, but there's some polarization vectors even in old-fashioned language. You have polarization vectors and momenta, and you have some d logs of kinematic variables. Okay? The claim is that on kinematic space, there is a unique projectively invariant differential form, no color factors anywhere, which is gauge invariant, on-shell gauge invariant, involving polarization vectors and momenta. Okay, and that form is actually the Yang-Mills, the full colored Yang-Mills amplitude. Okay, and now 2 claims. One, how do I get the Yang-Mills amplitude from it? Well, everywhere I expand it out as a form. Everywhere I get ds, 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 everywhere I get one of those guys, I replace it by the corresponding FFFF. And that's the way I go from the form to the full amplitude. Or B, let's say I want to get a particular trace. What I do is take this differential form on the full kinematic space, and I pull it back to exactly the subspace we defined for the associahedron. But that involves choosing an ordering. Right, so you choose some ordering, these x plus x minus x equations. You choose this ordering. You pull back this form that lives everywhere onto that subspace, and you get the Yang-Mills amplitude for that ordering. So there's this very intimate connection between kinematics and color, which then has many other consequences as well. It's related to the fact that gravity is gauge squared and so on and so forth. But at this most basic level, it appears that these forms are actually about color. And so the reason why I didn't see a real role for them so far is that I only told you about the story in a single ordering. But there's a natural extension of the story beyond the planar limit for all orderings. And this way of thinking about forms is kind of formizing or geometrizing color. The amplituhedron way of thinking about forms in momentum twistor space is geometrizing helicity. And so it's very strange. I don't know what to tell you. It's very strange that we have 2 very, very different ways of uplifting amplitudes to forms that have very different purposes in life. And we don't yet know how to combine the 2 of them, and we don't really know what the general lessons are. More generally, I hope it's clear that we don't have any we're like that famous Groucho Marx joke, right? We don't have any. You don't like our principles? We have other ones, right? You know, so we don't know. We don't have any principles in this business. We don't yet have any principles. We're just starting to get guesses, right, for what the nature of the questions are. But I still think it's rather striking that it's a very similar kind of question in very, very different settings, with a very similar flavor to them. And you know, it's not just pushing around equations and, you know, interpreting something from a pretty language, blah, blah. It has beef. It tells you things you didn't know before. You know, formulas that are true formulas that were not known before, that are exposed by this way of thinking about things. There's a third example. So I've told you guys about almost all the examples. An example we won't have time to talk about at all is in cosmology. So there's a question about calculating the wave function in the universe, or calculating the wave function in the universe in perturbation theory. You can think of this as a kind of geometry underlying old-fashioned perturbation theory in the quantum mechanics. Okay, and that ends up being associated with the polytope as well. So that's another question where there's something polytopal. Now it's something that has nothing to do with scattering amplitudes. That's just for something about old-fashioned perturbation theory in quantum mechanics, or computation of cosmological correlators in de Sitter space, or the flat space wave function in quantum field theory. So those are the examples so far that we've seen this kind of connection. But it's the same thing every time. The object lives in kinematic space. There's a positive question in kinematic space. There's a subspace, and there's a form. And that's the uniform thing in all the examples. I don't know. I mean, I would in previous years I would swear up and down that all of these things are very, very special to gauge theories of gravity and so on. But since we've seen this business for something as dumb as phi cube theory, I'm less sure. But I still somehow feel that Lorentzian physics is crucial for all of this stuff. I really doubt anything like it. Certainly, there's not a scintilla of reason to expect for some, you know, generic condensed matter system, phonons, blah blah. That anything nice is happening. I would be shocked if anything nice is happening. I think it has everything to do with relativity and quantum mechanics. But that's pure speculation. Okay, all right, gosh. Oh, Matt, that's what happened. That's what happened. I was wondering why it seems so free and easy. Yeah. So Matt is done. Matt is done. God damn it. Okay, great.